All right, good afternoon, everybody. Today's lecture will be on deep ontological networks. The overview of today's lecture will be as seen here. First, a very brief introduction and motivation as provided by the authors of the paper. Then also a very brief background on what we call ontological reasoning, because it might not be in everybody's background. So we'll talk just a little bit about the semantic web and what we mean by ontologies, because it's the basis of what the authors develop in this work. Then we move on to the meat of the paper, which is recursive reasoning networks, the tool that they propose in this article. And we follow the same structure in this lecture as the authors do in the paper. I think it's very nicely done. First, they develop the problem statement itself, and then instead of getting right to the inner workings of the model, they provide intuitions about how they work, and then do a little bit of a deeper dive. In this case, we'll see that the actual guts of the model are quite straightforward in the sense that they don't develop anything very new. So they take recursive neural networks almost out of the box. They just do some clever encoding of the parts so that they encode ontological knowledge. So it's very, I think it's quite it's a good approach to do it in this fashion. And then to conclude, we'll see a little bit about how they evaluated their model and the results that they obtained on practical instances. So for introduction and motivation, the authors focus a lot on human-like reasoning. So as they pointed out as one of the major goals of AI, and they claim that machine learning approaches typically entertain a quite informal notion of reasoning, as it says here, which is often simply identified with a particular kind of prediction task. This is the kind of thing that we see typically in machine learning papers, right? They say, I'll be focusing on detecting this kind of object in this kind of media, like cats in pictures, or some sort of activity in a video. And that's then they solve the prediction task by getting new data, previously unseen data, and seeing how well the developed model or set of models or tools does on this previously unseen data. On the other side of the ring, typically we can see this as two opposite poles. We have knowledge representation and reasoning, typically called KR and R, or just KR, where these approaches typically take reasoning as the application of some kind of mathematical proof theory. For instance, as we've seen in this class, first order logic, or some kind of machinery of that kind. And it's also well known that each of these approaches has its upsides and its downsides, right? So machine learning, as we've seen in papers in the last few years especially, they get good results, sometimes very good results, great, on specific domains. They handle noise very well. When we say noise, we mean when you have some sort of unexpected aspect in the input, like a picture where you're trying to detect if there's a cat in the picture and a whole bunch of the pixels are dead, for instance, that kind of thing. The solutions are typically scalable, but on one of the worst aspects of these approaches is that they're brittle. When we say brittle, we mean that when you change something slightly, even the noise is one good example, because there's a lot of research nowadays in the last few years, especially on adversarial machine learning, where you just add noise that is especially crafted, so it's not something that randomly occurs in the environment, but it's especially crafted by an attacker, so that, for instance, you can change the prediction for a traffic sign, for instance, instead of predicting a stop sign when it's obviously a stop sign, you can craft some noise to add, and it will predict that it's some other kind of sign, like a yield or a speed limit sign. So on the other hand, KR is very expressive. It's correct in the sense that if you can do a derivation like you do in first order logic, there's no doubt that that's correct. It's flexible usually in their representations, but typically not that scalable, nothing compared to the kinds of things that we see in machine learning. And noise causes major issues. So for instance, there's a whole area in KR dedicated to reasoning under inconsistency. When you have a database and rules, and there's a problem, there are problems inside the facts or the rules, and where constraints are not being met, and how do you answer queries? That's a whole area. And as we'll see in this lecture, this kind of thing is handled very well by machine learning approaches. So the authors propose recursive reasoning networks, as I was saying before, or RRNs, as a neuro symbolic model. And one of the questions that one might ask, and the authors themselves ask in the papers, why would somebody take a machine learning approach to reasoning? So that's also, we won't dedicate much to answer this question because it's one of the main issues that we're dealing with in this class. It's so combining machine learning and KR is now commonly regarded as one of the ways towards making significant progress in AI. So these approaches, as we've seen throughout the lectures, and we will continue seeing in the future, they're expected to allow leveraging background knowledge, for instance, to address the brittleness problem that we pointed out before, knowledge transfer. So when you have some kind of problem or set of problems already down, solved, how can you take advantage of that and solve a very similar problem? Learning from smaller amounts of data, one of the downsides of machine learning is that they're very data hungry. And also, of course, in the last few years, we've heard a lot about explainability. So symbolic inference is typically regarded as being more adept to explaining, because you have these objects in your hand that you can point to and say how you inferred. But they might also help, these neurosymbolic approaches might also help make these neural models more explainable if the relationship between both sides is significant. So the goal, the authors point out, is to employ state-of-the-art techniques from deep learning to manage the balancing act, in their words, and obtain the best of both these worlds. So we'll start then with a very brief refresher on semantic web and ontological reasoning, as I promised. So the semantic web, quoting Tim Berners-Lee from his 2001, already over 2 decades old, Scientific American article, he says that the semantic web is not a separate web, but an extension of the current one, in which information is given well-defined meaning, better enabling computers and people to work in cooperation. So we can distinguish 3 key concepts here. He's talking about an extension of the normal quote-unquote web, or what we now call Web 1.0. We'll see a graphic example of this in a bit. Information needs to be given a well-defined meaning. That's why it's called a semantic web. So semantics is referring there to meaning. And the goal is to enable computers and people to cooperate. So trying to bridge this gap between, this large gap between machines and humans. So the semantic web aims to offer standards that help leverage semantics-enriched data and knowledge at a large scale. So data with meaning, what do we mean by data with meaning? So a little bit of humor here. We can see what we say to dogs, and the owner presumably is talking to this dog, Ginger, and says, I've had it, you stay out of the garbage, and says a whole bunch of things to the dog. And what the dog hears is blah, blah, blah. Ginger only recognizes his name, right? And another from the same comic strip, Far Side, scientists trying to decode dolphin speak, and they're not doing very well. So this is kind of what we're up against when so the machines in this case would be the animals in the example. We're trying to communicate things through, sometimes to each other, but through machines, and we're not doing very well. So this is what the Web 1.1 looks like. So we have a graph, so that's why it's called the web, right? We have a resource, we have references between them, but this is what the computer sees. So it's understandable by us because we know what each one of these is. You can have natural language descriptions of them, you have documentation, you have all you want, but the computer can only read this. You can say, oh, okay, from this resource I can jump to this, or there's some sort of relation there. And what we want is something like this. The semantic web would say, okay, this resource here is a piece of software, this resource is a document, and this reference is actually pointing to the fact that this software uses this document, or that it depends on this other piece of software. This software generated this document, right? So you get the picture. This is also understandable by humans, the same as before, but more understandable by computers because we can encode what each of these relations mean and what these classes mean. We'll continue seeing a little bit more about these relations and classes throughout the lecture. So the semantic web stack, or also known as the layer cake, is depicted here. We have at the bottom things that have already been standardized, like URIs, the resource identifiers, languages like XML, data interchange languages like RDF, and up to query languages like Sparkle. Sparkle is a kind of like SQL, but for semantic web languages. RDFS to encode knowledge bases, rules, and ontologies. And I have it pointed out like a circle here because we'll see a little bit more about this. And if you keep moving up, it's still in research, the unifying logics, proof theories, trust, all of the things that make up the more complex problems. And you have crypto here as a traversal of everything up to this level. Implemented, we have user interfaces and applications that are in constant evolution. So if you look at this stack, it's pretty tidy, but if you go to the architecture of the web, it's not that. There's not such a direct mapping, right? So you have all of this kind of things that map back to the stack, but you have the users that interact through HTTP, HTML, that kind of thing, through different kinds of mashup sites, and at the bottom, these things that we just talked about, RDF, web ontology languages, Sparkle, and underneath all of the resources. So what are ontologies? We've been have been moving towards this for a few minutes already. It's ontology, the word itself, you can have you can find references in philosophy to this. It's ontology means refers to what exists, what is in existence in the world. So from computer science, from the computer science side, we can say that an ontology is a model of some aspect or aspects of the world. Another way of thinking about ontologies is the evolution of a database. So if you have a database, it's a set of facts, it's also a model of some aspect of the world, but we'll be adding much more stuff on top. First of all, it introduces a vocabulary relevant to the domain. So for instance, everything that has to do with auto mechanics, so the type of objects that you can encounter in this domain, the kind of relations, kind of classes, that kind of thing. Then it specifies a meaning or semantics for terms. So for instance, starter engine in the auto mechanics world is an engine, kind of engine that's part of the car's starting system, right? So it's the one that when you turn the key, it makes the classic sound that every car makes. Well, at least the non-electric cars. And it can be formalized by logical languages. For instance, if we take first order logic, you can say things like this. So for all X objects X, if X is a starter engine, then it is also an engine, is what's being encoded here. And there exists objects Y and Z such that the engine is part of Y, and the starting system is also part of Z, which in this case we don't continue, but it's presumably another aspect of the car or the car itself. So very, very simple ontology, so we can communicate a little bit about why they're useful. So let's consider artists, consider works of art. Artists can create works of art, that's what they do. A subclass of the class artist are the painters, right? So they typically produce subsets of works of art, which are paintings. So this subset of the creates relation then is called paints. And the same kind of thing for sculptures, right? Sorry, and sculptors and sculptures. These people sculpt sculptures. And what we're missing, the final thing that we're missing are the actual individuals here, right? So artist, work, painter, sculptor, those are classes in the semantic web lingo. The individuals are called instances, and the relations are called relations. So what can we do with this very simple ontology? So we can encode them in first order logic, for instance, or other kinds of formal languages. So for instance, for all objects X and Y, if X and Y, if X paints Y, then X is creating Y, right? That's the going up in the hierarchy. If X creates Y, then X has to be an artist and Y has to be a work of art. The same kind of thing for paints. We have the X is the painter and Y is the painting. So a fact like Michelangelo created La Pietà would be encoded simply like a fact in a database, right? Sculpts Michelangelo La Pietà. Michelangelo and La Pietà here are the individuals, the dots that we saw in the Venn diagram. And so if we only have access to that fact or that sets of facts of that kind, we can only answer simple queries like we do in databases, right? Like, what did Michelangelo sculpt? So in that case, we would get the Pietà, or who sculpted the Pietà, and then we would get Michelangelo. So it's kind of very basic kinds of questions that we can ask about this set of data. But if we have an ontology, then you can have derivations, or what we call reasoning. Typically, ontological reasoning is the use of derivations and then answering queries based on these derivations. So, for instance, who is Michelangelo? He's an artist and also a sculptor. What is La Pietà? Is a work of art and also sculpture. Do you know any sculptors or sculptures? Yes. And in this case, only just with that fact, we know Michelangelo is a sculptor, La Pietà is a sculpture. Or do you know any artists or works of art? Yes, Michelangelo is an artist and La Pietà is a work of art. So see, here we can see that Michelangelo is both in the role of sculptor and artist. So you can ask about both kinds of things. So this is the kind of thing that we referred to when we say ontological reasoning. Of course, this is a very simple ontology, very simple language as well, but there are very powerful languages in the semantic web, and typically the balancing act that they do is between expressivity, so the power that they have to represent different kinds of relations and inferences, and scalability, which is what we're after in the semantic web. Typically, when we said one of the key concepts there was doing all of this at a large scale, because the web is huge, so you have to be able to scale. So a few remarks before we finish this section. Ontological knowledge bases can then be seen as a way to simply formalize information or knowledge in terms of individuals, classes, and relations. Relations are typically either, in many languages in the semantic web, are typically only, like we saw just now, either unary or binary. And knowledge graphs, which we've heard a lot about in the past decade or so, are special cases of this kind of knowledge base, where individuals are mapped to nodes, binary relations correspond to labeled directed edges in the graph, and classes correspond to unary, it's a typo, unary vertex labels. So facts and knowledge graphs are typically stated in the form of triples, and we'll see this throughout this lecture today, where we have subject, predicate, object, and where this kind of, we'll see exactly how this is done in a little bit, where the predicate would be either the relation or the fact that the subject is part of a class, right? And it is very common in the semantic web to assume a fixed vocabulary, something that typically doesn't change. So if you're interested in auto mechanics, it might happen that something new comes out or some sort of new knowledge comes about, but typically we can say, okay, let's freeze the vocabulary and worry about the data typically being the one that changes. So all classes and relations at least are fixed a priori. So let's start with the central part of this article, which is recursive reasoning networks. And let's move towards what the problem statement actually is that the authors want to solve. So first of all, the language that they consider is a subset of data log. Data log is a very classical language at this point, where it's very, very closely tied to the databases community. And in the subset that the authors use in this paper, the relations have variety 1 or 2, like I mentioned before. We have no functional symbols, and we have rules with the symbol bottom or contradiction in the head that are allowed, and these rules represent constraints. So bodies that lead to something that can't happen. Rules are of the form, you have a conjunction in the body leading to an atom in the head. Negative constraints, like I just said, are bodies leading to a contradiction. And in both these cases, alpha and the betas are atoms, and n can be 0 or greater. So facts are just ruled without bodies. So we could have alpha where n equals 0 here. Would be a special kind of rule. Literals, as usual, are either facts like alpha or a negated fact like not alpha. And databases are just finite sets of facts. Here's another kind of example, but in this case in the data log language. So very similar to what I was saying before, adding the constraints that I didn't have, where we have things like if X is holding something, then X is human, or as it says here, only humans can hold things. And only objects can be held. So if 2 elements are in a relation. Here we use the underscore for an anonymous variable. We don't need to refer to it, but it could say here X as well. Then Y is an object. These classes are disjoint, so humans and objects can't have no overlap. That kind of thing. Here we have a little bit of an example of reasoning like before. Objects are at the same location as the one holding them. So if X is holding Y, then Y is at the same location as X. And then we have a few facts like Mary is holding an apple and Mary is in the kitchen. Then queries that we can ask is very similar to my example with Michelangelo. We can ask, is the apple a human being? This evaluates false. Is the apple in the kitchen? That kind of thing, right? Just using simply these rules and the facts. The language semantics is straightforward. I won't dedicate much time to this. It's defined as usual with urban interpretations, satisfaction of rules by these interpretations, logical entailment of facts by sets of rules. So we're trying to encode what is meant by truth in this language, basically, right? There's an interesting aspect here. So they use the closed world assumption. So negated facts can be derived using the closed world assumption. They also have this local variant where they consider this this notion of atoms being close to each other. But for those of you who haven't heard of the closed world assumption, it's simply saying that if I cannot model a fact, then I'll say that I will conclude its negation. So if I don't know about something, if I can't prove something, then I will prove that its negation holds. And the logical entailment is denoted with this usually use the turnstile symbol where this is like a bar instead of a tilde, but in this case to make sure that we're using this kind of the author's notion of entailment, we use this symbol like they do in the paper. Further, they assume that, like I was saying before, that the database is variable and of size k. We'll see why we need to specify the size. Sigma, which is the set of rules, is fixed, and the literal L will also be variable. We'll use that as the query, right, to make predictions. So then the problem, we finally reached the problem. So given a database D, a program or set of rules sigma on the literal L, decide whether the database and along with the set of rules derives or entails the literal in question. So the solution, the goal that we have in order to solve this problem is then in the context of this article is to derive a neural network that will be denoted with n sigma k with a binary output that then, given some sort of encoding of an arbitrary database of that size at most k and an arbitrary literal, then we can have this characteristic function where we have the output being 1 if and only if this holds true. And what the authors do is to craft these recursive reasoning networks that are designed specifically for this class of problems. We'll see that recursive or RRNs are a special class of recurrent neural networks, the recursive neural networks. So a few intuitions then. The idea is to replace, sorry, is there a question?
So on that previous slide, so the database of facts isn't passed to the neural network, only K, only the size of the database?
No, given, it says given an arbitrary database D of size at most K. You have to have the facts.
Okay, yeah, I was just confused from like the N of sigma K, but like the
Oh,
database.
here, yeah. Well, actually, wait, no, you're right. The neural network, we'll see this in a bit, it won't get the rules either. It will encode the rules, it will learn the rules and the embeddings of the individuals, and then given the literal, will tell you if it's entailed or not. So it is taking the database in the sense that it's encoded already inside as embeddings. Maybe it'll become clear, hopefully.
Isn't
a little bit
the
later.
difference, Jerry, that they use the database to create training samples and the rules to somehow extract the structure of the embedding?
Right. So the database, right? It's used to, as we'll see in a bit, is used to train, to learn the rules. Actually, it's the only thing that they use the data for. Yeah, that's right. Okay, hopefully it'll become clear in a bit. We have graphs and everything. So the idea is then to replace formal ontological reasoning with computing a deep neural network called an RNN that is trained relative to a particular ontology. So it will be independent of specific facts, and the vocabulary of classes and relations will determine the structure of the layers in the RNN, as we'll see. And as I was just mentioning, the rules are not provided, so they must be learned from the training data. And so that's why I guess in the notation we have N sigma, because the sigma are being learned, the rules are being learned. And the application of the trained model on specific facts will be done in two parts, two stages. First, we generate vector representations or embeddings as usual for individuals in the data, and then compute the predictions for queries based only on these embeddings. So learn a little bit of intuition on what the learning will be. So based on typically on the same idea as typically machine learning approaches are, that all information on individuals that are in this case both specified or inferable can be encoded in embeddings. And the process starts, the learning process starts by, like Paula was just mentioning, randomly generating initial embeddings for all individuals and then iterating over the data, updating based on training data to update the embeddings of the individuals involved. And this considers not just the provided facts, but also the possible inferences that can be made via the rules. So this clearly will involve going through all of the data, the training data, multiple times. But as the authors point out, it's essential. It's impossible not to do this because we want to encode reasoning chains. This will come up in the empirical evaluation explicitly, because we'll see what happens when we allow for less layers in the model and try and learn anyway. So the process itself, like I mentioned before, is the same as that for learning classical RNNs. It's just a way of the clever aspect of the paper is how the authors craft the layers so that everything works out. So this is the graph that I was promising. So we go through the data we separate subject, predicate, object, and as we'll see, we'll have an aspect, a part of the model that will look at. It'll look up the embeddings in both cases, right, and then update the model. So for prediction, the intuition is that the learned embeddings can then be used to answer atomic queries. So this is one of the, can be seen as a limitation of the model, because for now we can only ask atomic queries about the data that they are obtained from. So to be able to do this, the model includes multi-layer perceptrons for both relations between individuals and class memberships of, so for single individuals. And this second step is only uncovering knowledge that was already encoded during the learning process. And the idea then is to be able to unravel these complex relationships and be able to consider both relations and classes simultaneously, like ontological reasoning does. And one of the clarifications that the authors make explicitly in the paper is that triples are not treated as text. It's not like you're learning from a textual description of the database. So RNs are agnostic to the individual names. So they're trying to learn the relationship that they have, that the individuals have among each other in the database, and how to encode the possible inferences that you can make, but it's not important what they're called. So a few assumptions, like we mentioned before, and that the authors also make explicitly, is that we have a fixed vocabulary, so everything but the data, including the individuals, will be fixed. Relations are either unary or binary, and databases can be seen as sets of triples. So relationship R involving individuals I and J is simply I relation R and J, and a class membership is simply, we have like a member of specific, like a reserved relation where I is member of C. And negated facts are just simply encoded with different relation symbols. Here, the authors use the connective, the negation connective for the name. So this is why I use the quotes here. So not R would be the relation name. Maybe it would have been better to, instead of use the connective, say something like not, and NOT-R, and the same for member of. And for every knowledge base, we'll have an indicator function that simply maps individuals to vectors, and this will give us one if in the position for the member of, or the not member of, and 0 otherwise. So -1 is for negation, 0 is for I don't know, and 1 is for membership. And as is usually done in machine learning approaches, the vectors will just summarize all the information about the individual's class membership given explicitly in the facts. And the trained model will then be of the form, we'll have a probability distribution over what is true in given this this ontology, right? So where T here is an arbitrary query. You want to know if something holds, that will be a triple, and you'll get a probability distribution like it says here on the right-hand side that expresses the model's belief regarding the truth of the query. And managing, having probability distributions will allow for training using cross-entropy error. And the authors point out that during evaluations, they set a 50% threshold for queries to be predicted to be true or false. So if it's 50% or more, it'll be true, otherwise it'll be false. Another thing that the authors go out of their way to specify is that they use the term truth specifically because so instead of saying I want to know if this is true, if this holds, the relation holds, the entailment relation holds, since the neural network will provide a prediction even if the query is not provably entailed by the ontology. So it could, as we'll see with some extra experiments that the authors do to see how robust to noise the model is, sometimes the neural network will be able to provide a thumbs up for a specific query that the ontology wouldn't be able to do under the cases, the situation, for instance, of noisy data. Another interesting aspect is that training can be done using an actual database, or if you only have rules, as one of the data sets that the authors use in the evaluation, if you only have rules, you can generate a database based on those rules, generate a bunch of those, and use those as training data.
Another question.
Oh, yeah?
Yeah, so just from my understanding again, so the RRN will, you pass it a triple, it'll grab like the embeddings, and then it will pass those embeddings to an MLP, which will then output, like a softmax for like true or false, right?
Right.
So I'm wondering, where does this become like a recurrent neural net? Because, right, like in recurrent neural nets, like the output of time one or of time t minus one is also the input at time t. So I guess I didn't see that like come into play.
That's coming right up. Well, we'll see specifically how that comes into play in just a second. So right here in these update layers is where it's going to happen. So just to finish the setup, the model will then have individuals represented as unit vectors in real space, d-dimensional real space, and D here is a hyperparameter, so we have to decide how many dimensions you want to make use of for these embeddings. And the authors point out that it has to be based on the ontology, based on things like expressiveness, vocabulary size, and number of individuals. So this is a very important part to get right. And we'll have update layers that we'll see in just a second that will have to define two kinds, one for relations and another for classes. Since relations are in general not symmetric, you can assume that if I and J are in a relation, then the dual will hold, so Ji will also hold. We'll have in total 4 update layers, so for subject and object, and for positive and negative. And this is where the recursive aspect comes in. So they'll define a gated network, which is just kind of like I was saying before, a kind of RNN, where gates control how candidate update steps are applied. So a very brief refresher on what gated recurrent units are that the authors base their setup on. Simply like the person asking the question just now was saying, we have these update or forget gates, update gates in the GRU terminology. They will control how much of the new candidate is being incorporated, and so it's very complicated to go through this intuitively, actually, but this is simply doing this aspect of the networks that are taking they're doing passes based on the on previous inputs so that they can essentially encode some kind of context. So a lot of the intuitive explanations of these networks that I've seen typically use text, because I think that's what they were developed especially for, where they say, if I have a long sentence and I want to get right what the next output should be. If I'm generating text, for instance, then if I say, for instance, the tea in the cup, which was blah 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 blah, and then I continue talking about the tea, is hot, for instance. That hot refers to the tea, and in order to be able to keep this context, we have to be able to have this kind of structure, right? So in this case,
Quick question on the last one.
yeah.
Hi. Yeah, you mentioned that due to the the paper uses a recurrent neural network like a GRU due to the fact that the text you need to keep the context if you have a long sentence. But is there any reason why the work specifically used a GRU compared to, let's just say, an LSTM that is also a gated recurrent neural network and might probably be more apt for longer sentences, or was it empirically already shown that a GRU was much more better for this context?
That's a good question, actually, but the authors don't give any explanation in the paper that I was aware of. They just said, well, we need, actually, thanks for the question, because I talked about the text, but I didn't realize that I didn't say that the important thing is that the authors are doing it so they can keep track of the inferences being carried out in the ontology. So they're not dealing with text, they're dealing with inferences, right? So it's the same kind of thing. You need to keep track of what's going on in the inference so you get right the encoding of the rule. They don't, to my knowledge, differentiate between vanilla LSTMs and like neural networks based on GRUs. They just said, we'll do it this way. I presume that they tried out different kinds, and these were the kinds that worked better. Maybe it's buried in an appendix and I didn't see it, but that's a good question.
Another question.
I'm kind of like just along the lines of what he was asking. Like generally speaking, a GRU is like more efficient than an LSTM. So it's just it's like basically a GRU is just a simplified LSTM.
Yes.
In the paper, they cite another paper on like differentiable computing, and so there's a few different sequence models they can choose from. If you like dig around into references, it's probably fine answering that.
That makes sense on the efficiency, because I think the LSTM.
It just has like a few fewer like elements in its hidden state, but otherwise it's just an LSTM that's simplified.
Yes.
So in practice, it's more efficient and can learn just about the same things.
Cool. Thank you.
Great, thanks for the clarification. All right, so the way this is mapped in this is back to the paper, then we have then a gate controlling how much of the update is applied. Here we have this notation here referring to so moving like an arrow pointing to the left for the predicate, it's updating the subject's embedding, and they have one for the object, which is also analogous. So here we have the subject and the object, and P is the predicate. Sigma is just a logistic function, and here is where the calculation of the candidate update steps are carried out. And all of these are the model parameters, right? And then we have a simultaneous update operation where we update based on this triple, and we do both sides of the update. This is for the one-sided updates for relation. So for relation, so one-sided and then the simultaneous update. For classes, we have the same kind of thing. So classes are much simpler because they're one-sided. We don't have two individuals participating, and we don't even need a positive and negative version. We can just train one and then take the one minus to refer to the negation. So in this case, the model parameters are just these two vectors. And the algorithm, as I mentioned before, for doing this is not involved. So this is a quick overview of this. You can optionally have a matrix of initial embeddings. If they don't, you just randomly initialize, and simply for n iteration, there's also a parameter of the algorithm. You just do this update based on the triples. So for each of the individuals in the KB and each of the triples for the relations, you just do this update step, and then you're done. So this is where we can see materialize what we said in the intuitive part, where we had to go through all the data multiple times. So for prediction, this is where the MLPs come in for computing the prediction. So we have a single MLP, multi-layer perceptron for all of the classes. It's called MLP classes. And this MLP will just take a single embedding as an input and return the probabilities for the corresponding individual's membership in all of the classes, right? So for each of the classes, I'll have a probability. And then one for each relation, also in the vocabulary, MLPR, that will take, in this case, a pair of embeddings and provide a probability for the relation to hold between these two individuals. And the negation is just computed, as I said before, also one minus this output. So training, also not really much to say, is done, as I mentioned in the intuitive part, via samples of databases, which are sets of facts, as we call, that are associated with an ontology. This is the interesting aspect that Paulo was also mentioning before. So you have your training data can be considered to be a manifestation of the rules that they must obey. Okay, so only the DBs are used, not the rules in the training process. And this, I also briefly mentioned this, if you don't have any data, you can just use the rules to sample, to generate DBs for training. And this, the authors go into a pretty long discussion saying why this is a great idea, because it allows for a balanced use of all the rules that might not happen in a real database. And training can also be done on facts that only appear as inferences and not as facts in the database. That can happen perfectly. So for instance, with our very simple ontology, you could have, all of your artists encoded with their specific trades, right? So you had the sculptor, you had the painter, and maybe Michelangelo was never referred to as an artist in the data. So in this case, if you apply the rule that all painters are artists, then that data will be more representative of the inferences that can be performed with the ontology.
Really? Question.
Yeah.
So, since you have the rules and you're generating databases for training, so can we consider this as an unsupervised learning or semi-supervised learning paradigm? Because in those learning paradigms, we generally generate the data set rather than directly having labels and classifying them.
I hadn't thought of that, but I think it's still supervised, because you're generating the data and labeling it as okay because I know that it's true, right? It's I apply the rules and then just get rid of the rules, but the data, I'm not making anything up. I'm just applying the inference engine.
So more like active machine learning kind of thing.
Maybe I hadn't thought about that, but yeah. So then, even though a single training example is considered at a time, because but samples are complete databases, so the authors also point out that this corresponds to training with mini batches. And the procedure itself, as I mentioned a couple of times, is straightforward, and the overview is simply this high-level algorithm where you keep going while the evaluation error has not converged, and for each database in the training samples that you have, you generate the embedding matrix, you compute the loss, both from facts and inferences, update the model parameters to minimize the loss, and keep going. Right, so the training, there's nothing new here in the training process. So for the final part of the lecture, we have the empirical evaluation. So the authors considered a few data sets. We have these 7 data sets that are divided into synthetic and real. And the synthetic data sets are, they also refer to them as the toy data sets, mainly because of their sizes. So the number of class and relation types is quite low, as you can see here in the first 4 rows. And for the real data sets, we'll see what they are in just a moment. We have greater numbers here. So we have relation, they even have more, but they capped it at these, at least for DBpedia, at these numbers, just to keep it manageable. And then, they kept these numbers quite uniform for sample KBs. They kept it at 5,000, trying to see if that was enough to get good numbers. And a little bit more information on the positive versus negative classes specified in inferable classes and relations inferable for each class. So you can see that it's quite imbalanced. So you have the negative parts are much more dominating in general. So just to get a glimpse of what the data looks like, what the domains look like, at least this is one of the toy data sets. The family tree data set, the ontology says encodes all the family relations, right? So mother is a parent that is female, sibling, you have, the same parent and two different individuals, grandfather, we all know more or less what this is. So we have facts which state the gender, in this case considered as either male or female, and who's parent of who. And then some examples of inferences that you can do, like in this case, if you take Della and Huey, Della is a parent of Huey, and Quackmore is the parent of Della. So then Quackmore is the grandparent of Huey, right? The same kind of thing for sibling and great aunt. And in the graph here, we can see that it can get pretty complicated. There's 28 kinds of family relations. Not a lot of of these we generally don't refer to in our everyday lives, but they do exist. The other one is a countries data set, which is also quite similar, but it's a different domain, where we have the ontology says, which country is located in which region, who's a neighbor of whom, subregions. So region R has a subregion S, and who's, like I said, who's a neighbor of who. And some inference examples, for instance, Western Europe is a region of Europe, and Belgium is located in Western Europe. And because we have it here, then we can infer that Belgium is in Europe, which we didn't have in the facts. So quite simple. So DBpedia, for the real data sets, DBpedia encodes, it's a well-known data set, encodes knowledge from Wikipedia. It's massive, has thousands of classes and relations. And as I mentioned just a moment ago, the author is restricted to the 101 most frequent classes and the 518 relations that allow for the greatest number of inferences. There's not much discussion about this in the main body of the paper. There are more details in the appendices, however. The Claros data set is a catalog of archaeological artifacts, in this case much more toned down with 33 classes and 77 relations, but still bigger than the toy ones. And in both of these cases, the authors sampled using a subset of the original knowledge graphs using 200 individuals. So just to see how well they could do with this kind of sampling. And finally, the Unified Medical Language System, UMLS, it has, the domain is biomedical domain. It has 127 classes and 53 relations. And this is interesting because it has more classes than relations. The other, the rest of the data sets was the opposite. And this is one of the examples that I was mentioning where they only have rules. They don't have facts. It's just the set of rules. And the authors still can generate a data set of 5,000 sample KBs based on these rules. The results are very, very good. So as we can see here, accuracy, they do accuracy and F1 also for divided in the specified classes, the inferable classes, and the same for relations specified and inferable. And we can see that all of these numbers are quite close to 1. So it's a massive success for these tests at least. And the lowest numbers I think are here. So for countries, so for the S2 and S3 data sets, in the countries relation data set, they have the inferable relations are the ones that do the most poorly, but they're still very, very good at over 91%. The further experiments that I found the most interesting were the ones that I mentioned at the beginning, where they corrupted the test data. So in 2 ways. So first, taking away randomly, removing one fact that could not be inferred. And the other kind of corruption was the inconsistency, where they randomly chose one fact in each of the test samples and added the negated version of the same as another fact, so something that should not happen. And how they did was also not bad in a way, in one way of seeing it, but much worse than the numbers we just saw. So for the reconstruction of the missing information in DBpedia, they could do it 33.8% of the time, and Claros 38.4%. Inconsistency was much better, though, 88 and 96 approximately for these 2 data sets. This is, again, the spirit behind these tests is that if you do this on a classical KR approach to these problems, you'll just not get an answer. So that's what the authors underscore, where at least here you're still getting an answer. And in the case of inconsistency, you're getting a good answer. So it's, you could see it as a kind of graceful degradation where they're only randomly removing like one fact and choosing one fact and doing the negated version. So if I were the one doing the experiments, I would have liked to see how that keeps on degrading. But they had done a whole bunch of other experiments, so I guess this is for future work.
Got a question.
Yeah.
So I'm trying to understand the novelty of this approach. In the paper, they don't really compare this to anything but the neural theorem prover.
Yeah, it's coming up.
Yeah, and the results are relatively similar. So just for understanding, like if this would be done classically, right? So if we don't really care about necessarily the performance, so what would be like a set of algorithms that you would say use for these type of problems, and how would that performance compare to this, since they don't really mention it in the paper?
How would the classical approaches compare, for instance, for missing information for consistency?
Yeah, for this type of problem, for other ones, yeah.
Well, that would be kind of opening a whole can of worms, because there's, like I said, a whole area of KR for each of these, essentially. So it's not like you can just pick one and say this is the state of the art, let's compare. And again, if you're only removing one fact, I think the classical approaches would still do quite well, but it's hard to say, really. It's hard. You would have to really work hard at designing a fair experiment. So I think it's the novelty that the authors are driving at is, look, I mapped this to learning a kind of neural model that is, cleverly crafted. It works really well, at least for this language and for these data sets. And I can still throw at it the kinds of things that will typically really, really complicate things for classical approaches, where you have to develop these very involved tools to be able to get around and still be able to provide an answer. And it still does pretty well. I think that's, if I would have to make the case for the paper, that's what I would say. Maybe Paulo, you can add if you want to add anything.
We got a follow-up question.
Yeah, slightly different question. I was curious about the scaling of this approach. So basically, like, they have this hyperparameter D, and at the end of the day, right, they're using a recurrent network that is going to be unrolled across like the number of elements in your database. And when they sample for like up to 240, and it seems unlikely that they would be able to scale to like bigger than 240 because of vanishing gradients and other problems. So I'm curious, like, did they discuss this in the paper, and also like how would they address like scaling in general to like say a database with 1,000 predicates or something?
That's a great question. I also have the same kind of uneasiness when I was reading it. Like, how would it scale? They don't refer to it in the paper unless I missed it. So it would be interesting to see if it does scale better. I think it's one of its weaknesses, though.
Actually, another question, which is in a knowledge base, right? They use these like triplets. I'm curious about like, that seems like a common way to represent information in a knowledge base, but is that a limitation in any way, or is there like work that tries to get around that?
The limitation that one could say that exists in that sense is that you can only represent unary or binary relations, right? So that's one of the assumptions that the authors make, and it's one of the assumptions also that RDF makes. In RDF, there's a way around it, and they developed this concept of the blank node, where they say, okay, if it's ternary, it's a relation between the first guy and this blank node, which is another thing. And so you can like keep chaining it, and like saying, for instance, if I will give a gift to Paulo, what is that? It's a ternary relation, right? So it's Jerry, it's the gift, and Paulo. It would be Jerry giving the gift to Paulo, and that the gift to Paulo is another triplet, right? But that would be even worse in the sense of the scalability question that we just had, where it's injecting even more relations into the thing, right? So it is a limitation.
Got one more question.
It's a follow-up to the one of the first previous question was regarding with the scalability of an LSTM. I'm wondering, because due to the vanishing gradients, if you scale it up to more rules, could you possibly replace the architecture with like a transformer that is like a long, there's these different variations like long former in order to get scalability to these very long sentences, or at this case, these long database of predicates, for that.
That sounds completely reasonable to me. It's way beyond, I think, the scope of the paper, though, and it does sound like a reasonable approach. One thing that I would like to point out is that even though you can encode long derivations of rules, typically you don't see them in the wild, right? So you don't see like these very long chains being encoded. So I think it's reasonable to consider that there's an upper bound on the length of the derivations that you can have, of course, in detriment to the generality of the approach, but it won't come up in practice as much as one would think, and depending on the domain, of course. But. All right, so just to finish up, the authors, they provide a visualization of the embeddings and how they this TSNE embedding of how the individuals look like in the country's data set, essentially just to validate that the way that the model learns these embeddings makes sense visually, right? So you can see how they group together in ways that they make sense. Just take a look at the paper for this. The comparison with the neural theorem prover is one of the questions that we had. Also, the RNs come up on top, not by that much in some cases, but typically they do win. But the neural theorem prover is the kind of rules that they encode are restricted to positive foreign clauses, so kind of like a prologue. And the authors point out that it's trained on the same knowledge graph as the one that it is evaluated on, which is not ideal. And also it has performance issues, so we're only able to compare it, as we can see here, on the synthetic or the toy data sets. Last couple of experiments where they do the update, the number of updated iterations to see if they can get away with doing less, and also the number of layers per relation that they have. I mentioned this briefly, and you can see that for different kinds of relations which require, they call it hops, the inference steps that you have to do. So for father, it's just one. For sister, it's 2, because you have to go up to the parent and then go down and then check that it's female for the sister. Great grandson, up to 5 hops, and this maps quite directly to the number of update iterations that they have. So it's kind of like a validation of that, and also for the inferable relations with one prediction layer per relation, and one for all. So one for all is not enough, because you can see that it drops significantly in some cases the performance. So you have to actually have one per relation. All right, so finally, this is essentially COUTS level 4, where symbolic knowledge is compiled into a neural model quite directly. It has strengths. I think we discussed this during the questions, so it's elegant and it's effective. Very promising experimental results. I think there are a lot of more experiments that could be done to see how they do. Some limitations, not yet capable of producing explanations for the inferences, and data log is quite weak as an ontology language. If you compare it with like OWL, like semantic web languages, like also like data log plus minus existential rules, it is where they actually come up with, for instance, value invention, like saying every person has a father, and then you can do it, these kinds of inferences. These are not considered. So for future work, I think that they could incorporate other forms of reasoning also. This is mentioned in the paper, such as non-monotonic and things like argumentation-based reasoning. These are not at all considered. That's it.